We are used to thinking of artificial intelligence as something weightless, a sleek prompt box on a screen, living in an invisible space we call the cloud. But that cloud is anchored to the ground inside sprawling, heavy concrete server farms. AI infrastructure is the most physically demanding sector of the modern digital economy. Training a single large-scale model requires thousands of specialized, heat-generating chips running continuously for weeks at a time. This chart shows global data center electricity consumption climbing toward a massive milestone. By the end of 2026, total demand is projected to exceed 1,000 terawatt-hours. That is equivalent to the entire annual electricity usage of Japan. Every digital prompt has an immediate, heavy footprint in the physical world. This physical expansion is creating a sharp economic divide. While major tech operators negotiate corporate energy discounts for their facilities, residential electricity prices are climbing at their fastest rate in decades. The cost of this industrial growth is appearing on monthly utility bills in households across the country. Since 2022, residential electricity prices have risen by 10%, even as industrial prices in many regions have actually fallen. The gap between those who drive the new demand and those who maintain the grid is widening. This timeline illustrates a structural bottleneck. A data center is built in 2 years, but upgrading the grid for that load takes 4.5. To bypass delays, utilities fast-track upgrades, socializing those costs, distributing the bill for this rapid expansion across their residential ratepayers. In regions like Maryland and Ohio, wholesale electricity price spikes are already adding $16 to $18 to local residential bills every single month. Local communities are effectively absorbing the financial shock of global data processing. This pressure extends beyond the power grid. To prevent thousands of processors from overheating, data centers rely on massive evaporative cooling systems that consume enormous volumes of fresh water. This surge is accelerating. In 2023, data centers consumed roughly 17 billion gallons of water. By 2028, that number is projected to hit 68 billion gallons, a 300% increase in just 5 years. To find cheaper renewable energy, hyperscalers frequently build these facilities in dry regions where water is already a scarce and contested resource. In India, the crisis is uniquely acute. A strained regional power grid forces data center operators to maintain massive battery backups just to stay online during frequent outages. A single large data center can consume millions of liters of water daily. In cities like Visakhapatnam and Bengaluru, this creates a direct conflict with local residents, who must rely on tanker trucks for their basic water needs. It is a zero-sum game. Vital resources are extracted from local citizens to support computing power that is often exported elsewhere. The massive high-density infrastructure required for modern AI is now being used to manage the very resources it consumes. Companies are deploying AI-powered digital twins, virtual simulations of entire plants, to predict leaks and optimize water flow. In some facilities, these simulations have already reduced water consumption by 60%. Engineers are also shifting towards closed-loop cooling. In this design, water stays within a sealed circuit, constantly recirculating without any loss to the atmosphere, which can cut freshwater demand by 70%. But while technology can optimize the hardware, it cannot fix the underlying economic model that distributes these costs so unevenly. This is a form of rent-seeking. Large-scale tech firms are capturing private profits while shifting the physical and financial burden of their infrastructure onto the public. Without a change in how we regulate these facilities, middle-class families and water-stressed communities will continue to bankroll a trillion-dollar industry through their monthly bills. Solving this requires clear policy, specialized energy tariffs that reflect the true cost of large-scale loads, and mandatory requirements for water-efficient cooling technology. Securing local energy and water stability requires us to look past the digital interface and manage AI as heavy, resource-hungry infrastructure.